This is an initial test setup of the antenna IF assembly before the equalizer modification. This one happens to be serial number 5. So I set up a noise source, it's 2 to 18 gigahertz, and set the attenuation level to produce minus 28.8 dBm close to minus 29 dBm at this input connector. And if you follow through, there's a white coaxial cable that leads to a 90-degree adapter, a chow amplifier, 90-degree adapter, male to male in this case, 10 dB Krytar attenuator, and a power detector. This one is CONT-DET1 or continuum detector number 1, male to male barrel, 0 dB pad, Hittite variable attenuator, 3 dB pad, male to male barrel, MyTech amplifier, barrel, 10 dB 10 dB directional coupler, another Krytar, a second 10 dB directional coupler, again Krytar, and then CONT-DET2 power detector, preceded by a 10 dB and an 8 dB pad. These are select and test pads. You select them to get the desired voltage coming out. And the final output here is, normally it goes to the fiber optic transmitter. You could just barely see the SMA connector there. It's an Ortel transmitter. And there's a 3 dB pad right before that. And I'm measuring power here while adjusting the Hittite variable attenuator control voltage. So you can see that the power is, you read the top one, it's 10.22 about, and here is the control voltage for the Hittite. It's 2.42, so I'm gonna just tweak it slightly and make it 10.0, because that's the target value that we're shooting for. At least it was for the pre-modified version. And then here are the continuum detector voltages. So CONT-DET1 is 6.96 volts, and CONT-DET2, which is what the Hittite is servoed around, is 8.1 volts. Okay, in the previous step, we set the noise wave noise source to produce minus 28.8 dBm to simulate an ambient load presented in front of the millimeter wave receivers. And we set the Hittite variable attenuator to a control voltage of 2.45 to produce plus 10 dBm at the end of this connector here. And that simulates the set IF levels command that's done to servo the various attenuators in the system. And then I take various measurements at this location, and with the power meter still connected, I have a spectrum analyzer connected now, and produce this table here. And so various levels of attenuation. On the very left is the noise source attenuation, so 13 produced minus 28.8, and I adjusted the Hittite variable attenuator to produce plus 10 dBm, and that in turn resulted in CONT-DET1 and CONT-DET2 voltages to be produced here. And I saved the file as a CSV, so that'd be the spectral plot. But I also did it for a range of other attenuation values, so I could plot input power versus CONT-DET1 and CONT-DET2. And also look at the linearity relationship between input power and output power. Make sure that it's not compressed. And also did it for terminated. So with the input terminated, that means no signal coming in. It still produces a power of minus 27.7 dBm, so that'd be half a microwatt about. And that's parasitic noise generated by the antenna IF. And I also took a CSV plot of the noise flow of the spectrum analyzer. So now I have it connected the output connected to a spectrum analyzer, and it's settled down. Sweep is kind of slow. The start and stop frequencies are set to 0 and 20 gigahertz respectively. We're really interested in 2 to 16 gigahertz, but I wanted to show the entire response. And resolution bandwidth and video bandwidth are set to 30 kilohertz. And this is the ambient load condition. And of course, if I change the input attenuation, let's move it to 13 right now, and make it a large change, 19. So 6 dB change in attenuation. You'll see it should change by 6 dB. And you do see that here. And I saved each plot as a CSV file, shown on this table, and you can see the plots here. And the top blue plot, ambient load equivalent. Orange would be 3 dB down from that, and gray 6 dB down from that. And then the orange plot right here is the noise floor of the antenna IF with the input terminated, so no noise source going in. And then the blue is the noise floor, this bottom blue trace, the noise floor of the spectrum analyzer. So we're basically limited by the spectrum analyzer noise floor. The SNR is probably significantly better than what you see here. You can see, let's say at 10 gigahertz, it's 10, maybe close to 30 dB signal to noise ratio at 10 gigahertz, and it progressively gets worse as we go higher in frequency, but it's probably dominated by the limitation of the spectrum analyzer noise floor.